Okay, we are happy to have Ron today who will tell us about Morse theory of loop space of Hecke algebra. Okay.
Well, thank you. It's a great honor to speak here. So I'm going to tell about our recent work with Tian and Tian Yuan. And here's roughly the plan for today. So I'll start by kind of reminding how one can do Morse theory on path and loop spaces, and how one can introduce various string topological operations this way. And I will introduce this multi-loop homology with switches, and then I'll explain our computation of the associated Morse multi-loop infinity algebra in the case of sphere. And in the end, I'll tell about the connection with higher dimensional Hilbert-Floer homology. So we start with a smooth Lagrangian function on orientable Riemannian manifold M, which is fiber-wise convex and quadratic, which means the following. So roughly speaking, it means that along the fibers, it behaves like function of quadratic growth. But if we fix a splitting using Levi-Civita connection, this can be said that there exists a function L1 on M, and such that components of the Hessian, which are, well, vertical, and horizontal are bounded from above the way you would expect quadratic in the norm function to be bounded. And also we require it to be at least quadratic, so there is a lower bound of this bilinear form by some positive function L2 times the identity. But it all can be spelled out in local coordinates, just as some conditions on second partial derivatives, and it would be kind of the same statement. So examples of such functions is, for instance, just half of norm squared, or one can perturb it, say, by some potential which does not depend on a vertical direction. And, well, there are others, but these are the kinds you may think about for the rest of this talk. And then we consider the space of just paths between two fixed points Q and Q prime on M, or more generally, space of WM2 Sobolev paths. And this space is just the space of L2 integrable paths, which are absolutely continuous. Okay. This space has an action functional associated with L, which is given by this familiar integral, with which we usually associate a little Lagrange equation. And the critical points of this function on this whole Hilbert manifold are exactly the solutions of this equation. And for instance, in the example of half of the norm squared, we recover geodesic paths from Q to Q prime. These are the generators, and Morse theory would count certain gradient trajectories between these geodesics. So here, it's kind of important to note that even for that class of L, which are just sort of quadratic along the fibers, one does not always get that this function is even C2 on this space. So one may wonder how you do Morse theory here. And works of Abundandel and Schwartz and Abundandel and Meyer explain how to make Morse theory work. So in particular, there is the following theorem. So if we assume that all critical points are non-degenerate, then one can pick a smooth pseudogradient vector field on omega 1, 2, which would satisfy all the necessary properties to run Morse theory. So specifically, our action functional is Lyapunov for this vector field. this vector field is Morse for our functional. This pair satisfies Palais-Smale condition, which is what you need to say that you can compactify by broken trajectories. X is forward complete, and it is Morse-Smale, so unstable and stable manifolds intersect transversely. So here's an idea of this construction. So it kind of requires you to pick some cover of this whole Hilbert manifold, and in charts centered at not critical points, you may, well, with a standard trivialization there, you may set X to be kind of trivial in the neighborhood. So you just pick it to be the gradient at the center and just kind of linearly translate. In the charts centered at a critical point, you set it to be equal to the second Gateau differential evaluated at the center, and then you evaluate it on your gamma regarded as a tangent vector at 0. So although a function may not be C2, its second Gateau differential is still well defined. And well, again, because we pick it centered at 0, this thing is kind of smooth in the chart. And then you may sort of glue by a partition of unity all these vector fields into one global vector field, and you achieve this last condition by perturbing away from critical points. So this was sort of arbitrary. We could change it by a little bit and still satisfy all the remaining properties, and we can pick a separable Banach space of such nice perturbations. One additional technical result that we'd need later is that actually for L is above, one can pick such a pseudo-gradient so that all unstable manifolds actually consist of smooth paths and not just omega 1,2 paths. So first, one can show that each critical point is smooth. So let me give a sketch of how one can prove this lemma, but in a case where we work with a free loop space and L is time independent. So in this case, the unstable manifold, we're kind of in this Morse-bot setting because we can rotate along S1. So assume we have some gamma in the unstable manifold of some critical point. Then gamma is in lambda M2 whenever the path which is obtained by translations is differentiable in lambda M minus 1, 2. So let's start with some path in the unstable manifold which sits in lambda 1, 2. We know that this associated path gamma tilde is differentiable in L2 topology, but it still sits inside the unstable manifold by our assumptions. And since this manifold is finite dimensional, it sits here, but this map, which is non-embedding, restricts to an embedding there because it is finite dimensional. So therefore, this path, since it's differentiable with respect to smooth structure here, is actually differentiable in L1,2, and we get it that it's smooth in L2,2, and well, now we can bootstrap from here. Okay, so this result will be important, although maybe we could use some polyfold approaches, but okay, we work slightly more classically. So here is how one can introduce string topology operations using pseudo-gradients. So say we want, for starters, introduce Pentragon product. So this will be a chain map from a tensor product of Morse chain complexes for two path spaces, one for paths going from some point Q0 to Q1, and the other for paths going from Q1 to Q2. And well, it lands in paths from Q0 to Q2. Notice that we use the negative cohomological gradient here. So this is defined by sign counts of moduli space like this, which formally can be given by this formula, where this map C is a kind of standard concatenation from these product of spaces to omega 1, 2 of paths from Q0 to Q2. So pictorially, what you do here is you flow starting at some critical point gamma 2 for a little bit, you flow from gamma 1 for a little bit, then you concatenate these paths. You think of this path now going from Q0 to Q2, and you flow in a space of paths between Q0 and Q2. And you can think also of this sort of diagram here. Okay, so this is a cartoon just for some paths in R2. Let's say this is ambient space. More generally, we can introduce infinity operations. So if we have d critical points in these various path spaces, we may count Morse flow trees with concatenations at vertices. Well, I gotta say it's like actually weighted concatenations, and weights are assigned in a certain way based off the lengths of the internal edges. So these internal edges have some length, and it tells for how much you flow from here to here. And this is sort of a cartoon per se mu4 operation. So first, I would note that achieving transversality for this type of moduli spaces is possible if you introduce kind of time-dependent or flow-dependent perturbations, still landing in that X we fixed sometime earlier. And we only need to require that we perturb near the vertices of this graph. So we do not perturb near critical points, but somewhere in the interior, perturbations are needed. And in finite dimensional case, this sort of approach to Morse flow trees was pioneered by Fukaya and all. Later, this idea of working with pseudogradients was worked out by Mohammed Abu Zaid and Stefan Mesher. And also one needs to do certain gluing here, and the necessary gluing results were shown by Catherine Backrain. So sort of one, for instance, non-trivial gluing in one parameter family, so looks like this. In general, in zero-dimensional spaces, you would only see binary trees, but when you go to one-dimensional manifolds here, you may see trees like this, and there could be one parameter family going from this tree to this tree, so one needs to work out sort of kind of gluing like this. But this is sort of the only interesting phenomena besides kind of tree breaking that you expect to see in infinity operations. Well, in showing that infinity relations actually are satisfied. Okay, so this is how the story goes for just standard Morse theory. Now we would like to work with these multi-loops, or one should sort of think that we're trying to do here Morse theory of base path spaces on symmetric products secretly. So consider two tuples of kappa points in the configuration space of M. So basically just distinct tuples of kappa points. I fix this kappa for the rest of the talk. So for instance, kappa equals 1 should recover all what I already discussed. We set this space omega M2 of multi-paths from one tuple to the other to be a disjoint union over all permutations on kappa elements of products of paths from Qi to Q sigma I prime. So in the case kappa equals 2, there will be only two connected components in this space, which correspond to identity permutation and transposition. This sort of space has some interesting submanifolds. So namely, if we pick a pair of two distinct elements in M1 1 through kappa, we can pick out a Cm-1 submanifold in the product of this space with a segment, which is given by those tuples of paths which intersect, for which gamma I path and gamma j path intersect at moment of time theta. Notice that adding this segment here is important because, the evaluation map like this is Cm-1 map, and you can apply pre-image of diagonal in, say, M times M to show that this is a smooth manifold. But if you drop this space here, you would have a problem, and I don't think inside this space, this kind of thing where paths intersect at some point, it would be a really bad subset. Okay. Also, I'd like to say that, again, it is important here that there is a drop because we want to intersect these paths at some point, and differentiability with respect to theta is sort of lower than you would expect. So this is, again, sort of a common issue in polyfold theory. And using these diagonals, we can sort of introduce deformations into our standard Morse theory. So maybe before I explain this thing, if we just run Morse theory for these disconnected spaces, well, you would never leave one component into the other. So Morse theory for these disjoint unions is just like tensor products of previous Morse theory. But to make it slightly more interesting, we'd like to jump from one connected component to the other. And these diagonals serve as sort of natural space for that. So we introduce these switching maps, which cartoonishly look as follows. You just take these, you look at these two paths which intersect at this moment of time theta, and you replace gamma I with a path which travels along gamma I until theta, and then jumps onto gamma j. And similar thing happens here. So one should really think that we fixed some fixed set of a group action. Here it's just this transposition, and we kind of reflect it along this diagonal. And to stay within good level of differentiability, we unfortunately need to precompose. Well, one way to do this is to precompose with a certain reparameterization which has all its derivatives vanishing at those moments theta where things intersect. Well, maybe that's not the most beautiful thing to do, but kind of natural thing to do. This eta should depend on all of these theta, and you may guarantee it's smooth on the product of configuration space for all of these coordinates with our omega m2. And moreover, you can guarantee that it's restriction to all possible stratas corresponding to various partitions of L element set. They are also smooth, but it's not smooth on the whole sort of product of 0, 1 to the power L times omega m2. For sort of this reason, I don't think you can make it smooth everywhere. So this introduced certain complications later on. So here's the space we sort of want to count in our perturbed, deformed Morse theory. So we start with two tuples of critical paths, and we additionally need to pick this tuple of L elements of different pairs of distinct elements in our set kappa, and we also fix a permutation of L elements. Then a Morse flow line with switch-ins is a following tuple. So first of all, there are L plus 1 gradient trajectories. So kind of here how they go. There is this gamma naught piece, then there are L minus 1 finite length pieces, and there is another semi-infinite piece. So these are gradient trajectories for perturbed x that we fixed in the beginning. And most important thing happens at these kind of crosses, which are endpoints of all of these paths. So this is where we apply our switching maps. And well, in particular, the endpoints for each of the intermediary gradient trajectories should land on those diagonals that I just discussed. So this formula should make some sense. And well, we claim that you only need to perturb near these switching moments. So it may look like sort of the moduli for these markers where they leave sits on just a line, but secretly you may think of them as living on a strip because they have this 0, 1 coordinate. And again, it sort of matters where this 0, 1 coordinate shows up, because as we know that on the configuration spaces, we have these maps being smooth, and when say these two markers will collide on this strip, then we sort of may have some problems with smoothness. More generally, one can define Morse flow trees with switches. So if you start with now d plus 1 tuples of such paths, you may just mimic what we saw before, but now plug in switches everywhere on the tree, and now these switches can like travel around the whole tree, and you need to count Morse flow trees with switches. And again, perturbations are introduced as before near vertices, but also near our switching markers. So theorem that we prove that, again, there exists some choice of perturbations like I described, which makes these spaces into smooth manifolds. Well, this is a space of our Morse flow lines with switchings, and it has this dimension where n is dimension of the manifold. So in particular, each switch costs you dimension, but in 2 dimensions, a priori, it doesn't cost you anything. So it means that there could be infinitely many of those. And if we set first the CM0 to be just the standard graded module generated by our critical Morse multi-loops, we can introduce sort of a deformation of this module for now, where we consider completion with respect to a formal variable of gradient 2 minus n. So when gradient is equal to 0, this is just power series in h bar. And then if we define this mu1 Morse to be the count of all possible L's here of such sums where for each L you have to multiply by the corresponding by h bar into corresponding power. This makes it into a well-defined graded operator with gradient shifting of 1, and it is a differential. And moreover, there are A infinity operations which defined by these counts over all possible. Well, this should be gamma naught here, over all possible tree types. Okay, so a little bit about the proof. So we sort of already explained how one should introduce those perturbations to make everything transversely cut out. But here is what happens with compactness. So again, one non-trivial phenomenon that actually can happen is that two switch points will happen at the same moment of time along your gradient trajectory, and they can sort of swap order. But it is important that if they kind of come to the same point, this will introduce sort of a tangency at for the multipath on this level, and it would be of lower codimension, and any other sort of degeneracies with respect to partitions of the number of these markers, they will all be of much bigger codimension. So that's the only thing that can happen. And yeah, but this is the only problem. And the new kind of boundary phenomenon in one parameter families for trees is switches traveling through vertices. So like this here. And one needs to deal with this to show all the infinity relations. But again, these are the only problems. Okay. So now that we sort of have this theory well defined, let me talk about how we compute it. Maybe I would pause. Are there any questions at this point? Okay. So now we'd like to compute these infinity algebra in the case of S2. Let me first remind this definition of Morton and Samuelson. So they introduced these braid surface Hecke algebras for Riemann surfaces with one puncture. So this blue star here is a puncture, and say you have kappa fixed points on it. So you take a group algebra of the braid group of this punctured surface with respect to these two formal variables, and you introduce two relations. So first you introduce this HOMFLY-PT skein relation, which sort of should remind you what we were kind of doing previously, when you sort of flow from this position to this position, you introduce this kind of resolution there. So this is maybe motivation for what we were doing previously. And there is additional kind of more formal relation of this mark point. And then Morton and Samuelson showed that in case of the torus, this braid surface Hecke algebra is actually isomorphic to Cherednik's double affine Hecke algebra. And well, one reason why these braid surface Hecke algebra are kind of interesting. And Honda, Tian, and Yuan showed that for surfaces of genus at least 0, this A infinity algebra that I just described is quasi-equivalent to the completion with respect to H bar of this braid surface Hecke algebra, where you specialize at value c equals 1. Note here that this is a fake A infinity algebra, because for surfaces of genus at least 0, you can show that all based loops are actually all of index 0. So all geodesic paths are unique in their homology class. So this is just an algebra, and for that reason, so their computation kind of required computing only products for those geodesics. No, this is genus at least 1 because it's base path space. So for free loops, they would have problems, but this is base path space. So for torus, you still have that. Yeah, in homology class, there is unique base, like with a fixed starting point, on a flat torus. Yeah, but like, I guess computation for the free loop space for the torus may be slightly more involved, but we don't do that for today at least. Yeah, but thank you. Okay, so now S2 on the contrary, well, has a potential of presenting much more problems, because we can go around the equator for however many times you want in each direction, and it gives geodesics of all possible indices. So in particular, you need to a priori compute all the infinity operations, or you need to do something to compute that thing. So in the current work, we showed that this infinity algebra for S2, for some fixed tuple of points, kappa points on S2, is quasi-equivalent to the following dj h kappa. So first, it has kappa minus 1 generators in degree 0 and 1 generator in degree -1. So I remind that we use negative gradient. So pictorially, if we say just decouple these points a little bit, and well, we can assume that nothing really changes when you just move these points slightly away from each other. So you should really think that this all is happening in a very small disk. So each Ti is a standard kind of generator in the braid group, which goes like this. And x1 is exactly this one strand going around equator, and all other strands are trivial ones. So these are the generators. Now relations between them are as follows. So, well, this relation is maybe an interesting one. These two relations are just standard relations for the braid group generators. This is again another kind of boring generator in the sense that you can commute x1 with tj, where j is at least 2, but commuting x1 with t1 is actually quite involved. And differential is computed like this, and then extended by Leibniz rule. So we'd like to state as before that this kind of DGA is quasi-equivalent to something coming from skein theory, but unfortunately we cannot, because I don't think it was computed. So we raised this question whether one can recover these DGA as a certain derived skein algebra of S2, for instance, by computing appropriate factorization homology, say with values in ribbon, HOMFLY-PT skein category, in the sense of works of Cunningham, Safronov, and Jordan, and Ben-Zvi, Brochet, and Jordan. So we don't know, and it would be nice to, well, if something like this is true, this would be really nice that our Morse theory still coincides for all surfaces with kind of what skein theory produces. But this is, I guess, a conjecture or something like this. Okay, so here is how we prove this theorem. So first, we verify these various relations. So for instance, let me show how we can prove that T1 squared is equal to 1 plus H bar T1. So we just need to compute mu2 on T1 and T1 and see that it's equal to this sum. So let me give you a picture. This is our T1. We consider case just kappa equals 2. And then two T1s stacked on top of each other look like this. And this tree picture here is actually, well, there is no flow happening here and no flow happening here, because this is already like geodesics of index 0, so there is no flow there. So all you can do is just concatenate. And the moment you concatenate, you start flowing, and this is sort of a braid picture for this braid. So you can see that this will flow this way, this thing will flow this way, and they will cross at some point. So you can resolve at this point and kind of apply our switching map once. But this is the only thing that you can do. And you may also not resolve, and you will then just flow to the identity. So this is where these two terms come from. So this is kind of a very straightforward computation. Now let me show how one can verify that dx1 is equal to something like this. So from this index 1 generator, for the round metric case, there are two flows. One goes this way and the other goes this way. So the one that goes this way actually just travels around for some time, but it always stays in this hemisphere. So it will arrive to just the identity and will never cross other strands. So it won't introduce even a possibility for resolutions. But this strand will travel to here, and will when it will go further, there could be many crossings there. So as a braid, this position looks like this. And then one can show that sort of when you write this full resolution in a differential that we're counting starting from here, because we're in this kind of low energy mode, so it's all very close to just being strands, this full resolution would be equal to the class of gamma in the braid skein algebra. And as a braid, this thing is equal to this. This is just the standard braid presentation in terms of generators. And for that reason, these computation forms. All right. So, well, some other relations in that computation require more work, but assume we did these computations. This just comes from computing some products and some mu1s. What happens to all those higher infinity operations, and why we're certain this is a DGA? So one should expect that kind of all A infinity operations vanish for D at least 3, because, well, morally, we are deforming DGA for just sphere, which is just a sort of polynomial algebra on one variable. So you don't expect to see non-trivial deformations, but like we don't have a good proof of that fact for the round metric. And the cure is to consider Princeton metrics instead. So people study Princeton metrics for completely different reasons. They're interesting from dynamical perspective, but for us, they do the job in showing that this computation can be simplified. So consider Princeton metrics on sphere from Katok examples. So in polar geodesic coordinates, they can be given via this formula, and sort of what's important is this kind of term which is linear in vertical direction on the tangent space, and kind of geometrically you may think of introducing some sort of wind on a sphere, and this is also called Zermelo navigation problem. So now when you have a wind on a sphere, well, traveling with the wind is kind of faster than traveling against it. So this is sort of what happens. On the equator, you have two geodesics, and one of them now becomes much shorter, the other one becomes much longer. And their powers, so going m times around in each direction, would have lengths with respect to this metric 2 pi m divided by 1 minus lambda. So this gamma plus go in this direction is the long one, because, well, this becomes very small. And this one is short, this is just pi m approximately. So this means that at least below this action, we have this kind of linearity of length action with respect to index, which is sort of nice. And for a round metric, you don't have it because, well, going this way and this way is sort of the same thing. So their index kind of cannot distinguish, well, or at least action cannot distinguish those two paths, and they would sort of introduce problems. So action arguments can buy you for round metric. Let's say if you plug in only even, say, geodesics of even indices, then infinity operations vanish. But it cannot buy you when indices of different parities are involved. So yeah, now this allows us to show the following. So first, if we say that this AI kappa corresponds to where lambda is approximately 1 over I, cannot take 1 over I exactly, because it's better to be irrational, but like fix something like 1 over I. Then we, using that linearity, we can show that A infinity operations vanish in a significantly big range, and with bigger I, the range is bigger and bigger. Then there are quasi-equivalences between the corresponding A infinity algebras, given by sort of just some kind of natural perturbation from action functional for lambda equals to 1 over I minus 1 to lambda equals to 1 over I. And these are, moreover, isomorphisms in this range, and the higher A infinity, well, components of this A infinity functor vanish again in a significantly big range. So these FIs can be given by counting so-called two-color trees, which were introduced in the work of Thibault Mazouir. And these properties happen to be enough to show that there is a direct limit like this, and it is a DGA, and moreover, it is a DGA that we started with. So that's sort of how we deal with higher infinity operations. Maybe it's not the best way to do that, but okay, it's something that works. All right. Are there any questions here? Okay, so in the remaining time, let me talk about floor theory. So consider the standard Hamiltonian on the cotangent bundle of M. Now, the sort of corresponding objects in the Fukaya category to kappa tuples of points should be kappa tuples of cotangent fibers above those points. So sort of as before, we set this CW0 to be just the standard contributions from the robbed Lagrangian homology for pairs of these fibers. So elements here in this kind of tensor products are just tuples of Hamiltonian chords between these various fibers. And they would sort of project onto some paths between these points. And again, we consider a completion with respect to this formal variable. Now we use Q coefficients, unfortunately, but I don't think, for at least for this theory, I don't think this is a problem. Maybe with better methods, one can get integer coefficients. And then to introduce infinity operations, we consider the following Hurwitz type moduli spaces. So first, let me denote by RDB moduli space of D+1 puncture disks with B interior marked points. So here is a cartoon. And over this space, we can consider the space of kappa-fold simply branched covers from a certain domain to a D+1 puncture disk, such that the earlier characteristic of domain is equal to chi, the number of branch points is equal to kappa minus chi, and therefore if you set this B here to be equal to kappa minus chi, you get a natural map which kind of forgets the domain. So here is sort of a cartoon of an element of this moduli space. This sort of domain has a natural two-fold cover, which is branched at a point like this. Okay, so with these spaces, we can introduce our infinity operations. Again, the formula is pretty similar to what we saw before. We introduce H bar to the power number of branch points. So again, these sort of branch points on the floor side should normally correspond to the switching points on the Morse side. And these moduli spaces, they count curves from a certain domain F to D times T star M. So these can be written as pi V, just using these coordinates. So pi should be an element of our moduli space, and V should solve a perturbed J-holomorphic equation defined in terms of certain floor data, which depends on this moduli space. So basically, we introduce domain-dependent floor data on this whole Hurwitz type moduli space. In this way, we achieve transversality. So theorem that we prove is that the obtained infinity algebra for this tuple of cotangent fibers above kappa points is quasi-equivalent to our Morse multi-loop infinity algebra. And the map here pictorially is given as follows. So let's first look at f1 of this functor. It counts sort of trajectories like this, where half of the trajectory corresponds to a kappa fold cover of a half strip with condition that on this boundary it is sent to the zero section, and after that it travels along half of the Morse flow line with switches. And higher infinity operations are given by buildings like this. So on top you have sort of a bunch of kappa fold covers over various disks. So this is sort of a disconnected curve. And on the bottom, you have not a tree, but a shrub, because it kind of cut it in half. And you need to sort of count all of these buildings. And here is sort of a sketch of the proof of this result. So first, for kappa equals 1, it is a result of Bozaid, and it's kind of a variation of Viterbo isomorphism. Now for kappa greater than 1, the sort of, at least for f1, the main interesting phenomena that happens is when these sort of switching points, they travel to top and become now branched points. So the picture, again, a cartoon for a curve in this position is as follows. So it exhibits a hyperbolic boundary node here. And if you go to the left on the curve side, you should just think of, from perspective of this curve, this is just some self-intersection of the J-holomorphic curve. And when you travel on the right, this is a hyperbolic boundary node. So in particular, we need this the gluing result for hyperbolic boundary nodes. So local model is given like this, and the inaccurate proof of this sort of classical result, because classical in the sense that it's very similar to the standard interior nodal gluing, but now there is no kind of rotation parameter here. And this result is shown by Hershey and Hachtenberg. They show also the more interesting result of elliptic boundary nodes, but we don't need that. And so these analyses show that F1 is a chain map. Now, if we set H bar to be equal to 0, this recovers a quasi-isomorphism just using this result, because again, all the branches and switches go away. So it's just tensor product of the previously known map. And because F1 is a deformation of this result, just kind of simple algebra allows one to show that this is a quasi-isomorphism. And they shown that F is an A-infinity functor requires a couple more gluing results for this sort of caps and trees, but those gluing results are very similar to already known gluing results, which showed up in the finite dimensional case in works of Bozaid. Okay, I guess I'll stop here, and thank you all for your attention.
Thank you. Are there any questions?
Oh, maybe can you say about you mentioned that there's like some connection to like this derived skein algebra, and maybe can you say a little bit about what that is and what maybe there's some sort of bigger picture that's expected to happen at play here?
Yeah, so okay, I can say for what it is for S2. So so there is this excision that is shown in, or at least used in the works that I mentioned, and it's shown by Juliet Cook. So it kind of allows you to compute this skein in infinity algebras by just say, if you know how to compute it on pieces, then, and they sort of intersect along this ribbon here, then the skein category or skein algebra that you obtain can be computed from pieces here and here, and the map from the ribbon. And these sort of computations, for when valued in temporally Lieb ribbon category, which is just also equivalent to the category for quantum of representation of quantum group of SL2. These being computed for surfaces, but so this gives you a Kaufman bracket skein algebras for surfaces, but for HOMFLY, for the corresponding like HOMFLY ribbon category which you assign to a disk, I don't think these computations were done yet. So one could try to do that for just this pair of disk and one ribbon, but I guess to obtain something derived, you need to do these computations where you treat these ribbon categories not as two categories, but as infinity categories. So that's just a guess. Well, I mean, this computation can be done, and hopefully it recovers our story. And I guess more general picture, one should wonder what happens in 3 dimensions, but in dimension 3 you should get some skein modules, and I'm not sure we have kind of Morse-theoretic answer to that story. I'm not sure that kind of our infinity algebra would recover wouldn't recover skein module, but I'm not making any conjectures about this.
Do you have in mind some geometric applications, like to Riemannian geometry, to some dynamics, whatever kind?
Yes, so I guess so one should really think that there should be some actually sort of more general picture here for deformations of path spaces of orbifolds, and we may hope to give some geometric applications for various questions, say about geodesics on orbifolds. So that's, I guess, the direction one could hope to go from here. And I guess I should mention the recent work of Max Smith and Zeffadini, where they define sort of a related invariant using global Kronich charts for orbifolds, and they reprove simplicity conjecture for the group of homeomorphisms of surfaces.
So when you say orbifolds, do you mean symmetric products of, I mean, the original space on which you do multipaths or something else?
Yeah. So here, I guess we do it just for symmetric products, but I guess we would hope to generalize it for any kind of, say, global quotient orbifolds. I mean, like one just need to. So here we sort of morally used the case where codimension 1 sort of stabilizers are just kind of symmetries with respect to certain submanifolds, but if, say, local stabilizers are not Z over 2, maybe something more interesting happens. So, I mean, this should be worked out, but one can expect that still certain counts for this all possible switches that can be introduced by this fixed loci. So one should hope to give some count like this.
Thank you.
What's the dependence of the infinity algebra on the Princeton matrix? Say something about it?
Yeah, so again, I guess I sort of rushed through this. So essentially, up to quasi-equivalence. So for instance, for using just the floor side, we know that kind of choice of this L is not really important. And I also use this kind of on just the Morse side, you can count these two color trees to show that these Morse infinity algebras are quasi-equivalent. And Mazuya shows this just in finite dimensional case where you have two different functions on a, let's say, compact manifold. Then you can associate these infinity algebras. They are quasi-equivalent by counting these two color trees. And two color just means that somewhere in between, in the middle, you swap from like gradient trajectories for one function to gradient trajectories for the other function. So we sort of use these maps for our argument to work.
Thank you. So and can you do something with filtration? Like
You mean like action filtration?
yeah.
Yeah, I mean, you definitely, well, I mean, you should expect to do, because all this well, the action still decreases along this more trajectories with switches. So yeah, one should expect that whatever you do in a kind of standard setting with, I don't know, like barcodes, etc., should be applicable here.
Interesting. Thank you.
Okay, so if there are no further questions, let's thank Roland again. Thank you.